Hi everyone, my name is Neumiller, and for my capstone research, I study cadmium selenide quantum dot solar cells with Dr. Sunskis. I know that's a mouthful, but in this presentation, we'll go over energy and electricity, why renewable energy is important, how quantum dots work, and finally the research that I did. So to get started, we need to talk about energy and electricity. As you obviously know, we use electricity and energy all the time in our everyday lives. It's how our world functions anymore. So as you probably know, energy is putting in work into something. And to generate electricity, currently we burn fossil fuels. So I'll direct you to the graphic on the screen. As you can see, this is using coal, but we burn the fossil fuels and it heats up water. That water turns into steam. Steam is directed through pipes and it spins this giant turbine. And that turbine in turn spins a generator, which generates electricity. The electricity can be directed to be used, like directed through wires, or it can be stored in batteries, or that water and coal can be stored for future use to spin a turbine. So we can store it or use it, and this goes the same for renewable energy, such as solar, wind, nuclear, or hydropower, or we can plug a dam, and then when that water is released, it spins the turbine to generate electricity. A vast majority of our energy today comes from burning fossil fuels such as coal and natural gases. However, this isn't necessarily sustainable or healthy for ourselves or our environment. So as you hopefully have heard, we are in a climate crisis and global warming is happening, and this is because we're burning those fossil fuels. So in this graphic, you can see that energy enters and exits Earth's atmosphere and Earth's surface. So the big yellow arrow coming from the left side is energy absorbed by the atmosphere, and this comes mostly from solar radiation. So some of the energy, that solar radiation, like heat and light, are reflected by our atmosphere before it even reaches our surface. Some of that is reflected and absorbed at our surface, just depending on what it hits and depending on the chemicals in the air. So when fossil fuels are burned, they release greenhouse gases, especially carbon dioxide. These gases collect in the atmosphere and they add a layer of heat trapping to our environment. And so more heat, more energy is kept within Earth's atmosphere instead of radiated back out into space. And this is where global warming happens, which in turn increases temperatures and causes climate change, such as rising sea levels because of the melting glaciers. Weather patterns are changing, more severe weather is happening, and other effects that we're seeing in our daily lives. And for these reasons, we need to transition into more renewable energy, and research to make that energy more sustainable is necessary. So solar energy is a version of renewable energy, and we'll be talking about that for the rest of this presentation. So most solar panels that you'll see on houses or in solar fields use properties of compounds to direct electrons through these wires. So you can see on the left here is kind of a structure of the two materials they use, and then the right, it shows how those solar panels work. But basically there's an N-type and a P-type structure. So N-type structures have an extra electron, like you can see in the left diagram here. And then P-type have like a hole where there is like a missing electron in the compound. And so by layering those two, when light hits electrons, they get excited and they move around. And so the layer with extra electrons, those electrons can be directed into a wire, and then the layer from the holes, it forms a cycle of moving electrons, which is what a current in electricity is. So most solar panels today use these silicon type structures. So a little background on more solar energy. So there are multiple generations or multiple types of solar cells. So current solar cells, this first generation is what I just explained in those silicon solar cells by directing those electrons from the N and P type structures. And these use like mono and polycrystalline structures, which is basically what I explained. Second generation solar cells use thin film semiconductors, which is kind of the first step into using film semiconductors, which I'll talk more about with quantum dots. So these next generation quantum dots focus on something we call the band gap, which is in this diagram on the right side of the screen. So every atom, every element has a band gap, and that's when electrons are resting in their valence stand, and when they get excited, like when light or energy hits them, they jump into this conduction band, and the distance between those two is called a band gap. So quantum dots are nanoparticles that are super small, and cadmium selenide has a very large band gap to begin with. And so that makes it ideal for capturing the solar energy because those electrons jump higher and absorb more energy. But what's really cool about cadmium selenide and quantum dots is we can control the size of those dots. So as you can see on these colored arrows, as the quantum dot itself gets smaller, the band gap gets larger. And because it increases surface area, and like I said, these nanoparticles are really controllable in the laboratory, and we can control the size, which controls the energy and size of that band gap. So we'll be studying the effect of DDT, not the pesticide, but 1,2-dicatenyl on these cadmium selenide quantum dots. So DDT is this chain, basically a hydrocarbon chain. And the next slide, I'll show how this interacts with the cadmium selenide dots themselves. But in this graph on the left, this was research I performed 2 summers ago in the lab, but you can see that depending on how much DDT we add, it changes the size and the photovoltaic properties of these quantum dots. So this is with no DDT added, which research on these quantum dots has been done before, and their efficiency in lab testing is about 11%, which is not ideal. But the more DDT we add, it shifts where these quantum dots absorb the light and energy that hits them. So with a higher DDT concentration, we shrink, make the quantum dots smaller, and we have a left shifting absorbance data as shown in this graph. So what does CD actually look like and how does it work? So in the first part where before we add DDT, these surfactants, these like kind of tail things, surround this like quantum dot in the middle. And these are being pulled off when we actually do our research, but I'll show pictures of that later. So when we add DDT to this, it adds another surfactant that competes for space around the DDT. And this competition, in theory, apparently shrinks the size of the quantum dots as we've seen in the data. So let's talk about the experiment that I performed and how this works. So I'll go over kind of like some of the chemistry and how this works. So we do all of our experiments in under a hood, and this is called the Schlenk line. It's basically a gas and vacuum manifold. And so this is important because it protects our experiment from being exposed to all the particles in the air, but especially oxygen, so our particles and materials don't oxidize. It allows us to have a completely controlled atmosphere where we know what's going in and out of our like beaker. And so in this right image, it kind of shows you how this works. So there's a line where gas can go in and out. We use nitrogen in our lab. And then there's also a vacuum pump set up. So when we first put our flask in it, it's all sealed up. And we vacuum all the air out, and then we start pumping it with nitrogen. So we're in a completely nitrogenated environment for our experiment. So let's talk about the experiment I actually performed. So in this chart, you can see the reactant and then the amounts of things I've added. So let's go over the reactants. First, we have CDO, which is cadmium oxide. It's like a red powder. And cadmium is actually pretty carcinogenic, but in the lab, it's not, we don't use a ton of it. Oleic acid, octadecene, and then DDT. They come in these big bottles that I'm kind of covering up here, but they're all just clear liquids. So we add those to our round bottom flask first. And as you can see in this picture, our flask is covered with a stopper on one side. In the middle here, this tube is linking it to the Schlenk line, so I can control the atmosphere that's in this flask. And then finally, we equip it with a temperature because this gets up to over 220 degrees Celsius. And when it hits that temperature, obviously the initial solution is going to be kind of this murky red because of the cadmium oxide. But once it hits that 225 degrees for a few minutes, it becomes clear. And that's this image that you see here. This is when we add our selenide. And selenide is kept in solution in our glove box. It's this clear liquid in the bottle here. And then when we add that, it immediately turns like a reddish orange color, depending on how much I add. In this picture, it looks like I added 0.4 millimoles because it's orange. So that's the initial synthesis of our quantum dot solutions. I then extract those from the flask. They're cooled down and kept into a vacuum test tube, but then we have to crash it. Crashing it basically means that we're extracting our quantum dots from solution and concentrating them. So we use ethanol to do this. It alters the polarity of the solution and causes the non-polar quantum dots to fall out of the now polar solution. We dry off the extra liquid, and it turns into this little dot that you can see on the right. It's kind of like just a blob, but it looks pretty cool. On the left, you can see these are the 4 colors that we create by using left to right 0, 0.2, 0.4, and 0.8 millimoles of DDT. So it's really cool. You can see not only in the data in the graph, but actually in the physical quantum dots, the differences that we're making by adding various amounts of DDT. So after we crash it, we'll suspend the quantum dot that we've isolated into toluene to make our solar cells. So to make a solar cell, we do spin coating. So in this first image, kind of in this layered section, this explains what we're actually making. So we have glass that we've pre-ordered, and it's a layer of glass with an ITO layer, which is indium tin oxide, but it's basically just a conductive layer. And on top of that, we put our cadmium selenide quantum dots, and then later we'll go over how we actually put our contacts and wires on. And then this voltage travels between the aluminum contact and this ITO glass through our quantum dots. So spin coating is kind of the same theory as like a merry-go-round. You spin things really fast and they spread out. This image in the middle kind of shows how that works. We disperse or we deposit our quantum dot in the middle, and then it spins it and it disperses it. Should be into an even layer. We kind of had some trouble with that in our processes, but I'll go over that later. So then we let that dry on some heat for a while, and our quantum dots are ready to actually be used as solar cells. So resistive thermal evaporation is how we put that aluminum contact, like you can see here, onto our cells. So this is my favorite lab partner, Louis the Minion. But basically it's a giant glass dome that's connected underneath. So this is the middle picture here is inside of the dome. We have this basket that we put aluminum chunks into. We set up our solar cells with a mask over them. So we only get aluminum deposit on a small section of our cadmium selenide layer. And then Louis the Minion, a resistive thermal evaporator, uses really low pressure and a high electrical current to create an environment where that aluminum in the basket can melt, and it melts so fast and so hot that it just evaporates immediately and coats everything in there, including our cells. So the end product is in this right picture, not the wires, we haven't put those on yet, but this aluminum square in the middle of the cell is the contact that we've created to create that system between the ITO layer through our quantum dots. So once this is completed, I attach wires with just a silver alloy on a clean section of glass and that aluminum contact. And that is a completed solar cell. So next we'll go into testing and data. So UV vis testing, or like UV spectroscopy, tests the absorbance and fluorescence of the quantum dot solution ourselves, not the wires and the current going through our solar cells. So absorbance tells us the wavelength that the solution absorbs light at, as you would imagine, and fluorescence tells us the wavelengths the solution will emit light at. So in this first graph up here, you can again see the 4 peaks. I didn't label these ones, but you can again see 0 DDT, 0.2, 0.4, and 0.8 as we talked about previously. So this shows that our quantum dots and various levels of DDT do in fact impact the properties of these quantum dots. Next up is fluorescence. This graph is a little wonky because 0.4 is over here, but you can still see the shift from 0.2 and 0.8. So challenges in this research. First, obviously it was a big learning curve for me, never having worked in a lab before, but I've worked in this lab a couple summers ago and then this year to complete this research. But some challenges we experienced was using the spin coater to deposit our film. It turned out that our film was way too thin and it wasn't consistent across the entire glass plate. And because of that, when we did solar illumination testing, basically we hooked the wires up and shine a really bright light to mimic the sun on it. We actually ended up frying our contacts. And so in this picture on the right, we've deposited a much thicker layer of quantum dots onto the solar cells. And so in the future, that should eliminate that issue. Future work in this laboratory will complete the testing to test the current and ultimate efficiency of these solar cells. But hopefully they do reach an efficiency that's comparable or greater than the silicon solar cells that are currently used. Those solar cells, panels that are currently used in industry today average about 25% efficiency, but these quantum dot solar cells are estimated to reach about over 60% efficiency. So hopefully laboratory testing can reach that. This left picture is kind of a cool picture. The quantum dots are really fluorescent when they're held up against a black light. So that's just kind of cool. Thank you so much for watching this if you tuned in. Here's some pictures of me in the lab. I kind of covered this one up, but I stole Dr. Jensen's bear at one point. It was really cool experience to be able to work in a lab. I learned a lot more beyond, a single lab practice in a class and how to use a shrink line. I got to work in a glove box, which is just like a cool nerdy thing for us scientists. And I learned a lot more about inorganic chemistry than I probably memorized for class, and a lot about quantum dots and solar energy, which is really cool and something I'll carry with me forever. I am graduating in a couple of weeks here, and I'm actually going to law school instead of pursuing a science graduate program. But my dream is to work in sustainability and climate solutions, and so this experience will impact my future. If you have any questions about this experiment, please tune in to our Zoom next week, and thank you so much.